Well, let's take a look at our last section of Unit 1. Valence electrons, you've heard me talk about that a lot. And ionic compounds I've mentioned briefly. I think we were talking about empirical formulas. So valence electrons really determine the charges. Get used to the patterns that we have here. Most of them are predictable, but some of them will have multiples. As you can see, the D block, there's nothing really concrete in here. But we have predictable ones that you remember from your patterns from previous classes. All right, make sure you get those patterns down because you're going to be using those going forward. So things next to each other act similar, as do things in the same group. So items behave, when we talk about chemically and physically in a group, due to their valence electron attractions. So all of these are noble gases, and the noble gases have full outer energy levels. And that gets more reactive due to the radius. So things down here are much more reactive and receptive to taking on, let's say, things very electronegative because their outer electrons are less attracted because they're much larger. Things down here become more reactive because, again, those outer electrons are much further away, much less attraction, less ionization energy, and so on. Elements next to each other are more likely to behave elements than further away. So sodium is next to magnesium. Neon is next to chlorine. Those are going to be more likely to react similarly, although I shouldn't actually say that because these are inert and don't react very well. But things like sodium and magnesium are going to be similar in reactivity than something like sodium and barium, or sodium and selenium way over here in group, which one is that? Group 16. So things similar or near each other are similar in their reactivity. Now, we've talked about what electron configurations are. We're going to look at these for ions. Remember, ions are atoms with a charge. Doesn't have its normal number of electrons. If it did, it'd be neutral. Atoms want to look like double gases, so they want full and sp orbital set. If you're a cation, you lost electrons, which means you have more protons than electrons. More protons than electrons, you're going to have a positive charge. Anions, gained electrons, less protons than electrons, as shown, negative charge. Now, how do you know which happened? Look for the closest noble gas and adjust your number of electrons until you're at the closest one. Let's take a look at that. So, lithium, I've got 3. Closest noble gas is going to be helium. I'm going to lose one to look like helium, be Li+. Calcium, closest one is argon. Going to lose 2 electrons to look like argon. Losing 2 electrons, I'm positively charged. Phosphorus, its closest one is argon. Going to gain 3 electrons to look like argon, hence it's 3-. Now, which ones are you removing? You're always removing highest energy level electrons first. Okay, so those are the energy levels, the numbers in front, the coefficients of our electron configurations. We don't remove electrons from the orbitals in the same order that we fill them in, so be careful with that. Once orbitals have electrons in them, their energy levels shift around. So really highlight D and F block elements as ones you want to keep an eye out for. So we have lithium. You see there's no charge, 1s2, 2s1. Making it like helium, you get Li+. Highest energy level electrons first, right? The 2s, because that's 2 is in the second energy level. Furthest away, lowest attractive force, therefore easiest to remove. Calcium to calcium 2+. Highest energy level is level 4. When it gets removed, it looks a lot like argon's electron configuration. D blocks are transition metals. They can make several different charges. Now, in the one that we're using here, we're not going to lose 3D because 3 is an inner electron, right? A core electron. It's going to lose the higher energy level first. In some books, they put the 3D before the 4s, but that becomes confusing when you think of how do these things fill in. So to become copper 1+, this becomes 4s1 3d9. Again, loses those electrons first. To become a 2+, it loses the other electron. So this is how copper can be copper 1 or copper 2. But again, it loses the highest energy level first. No matter what, take electrons from the highest take from the P, then the S, then come back to do the D, which I can't imagine too much happening from there. So taking a look at first from gallium, here's its normal as an atom. Then it becomes a 1 plus as an option because it lost the 4p. Then gallium lost one of the 4s's. Gallium 3 plus lost the other one. Then gallium 4 plus would lose a d electron. All those, again, look at the coefficients in front. Now we have the little bit of opposite. They talk about an excited atoms. And these can come up from time to time. So this, you may or may not have seen the idea of flame tests when they put in a small sample, in this case sodium, into a flame, giving it energy, exciting electrons up to a higher energy level, and when they fall back down, they release a wavelength of light. We'll talk about this, I believe, in our next unit. So we've looked at ground state and ions, those ones that have lost or gained electrons, right? However, there's the idea of excited atoms. These have higher than normal, but they're incomplete. So let's look at sodium. Sodium is this. Sodium ion is this. You saw one that's lost one electron. Excited can be any of the regular taken up to a higher energy level. So instead of this one being 3s, it took it up to 3p. Instead of this one being here, one of the inner electrons from p jumped to d. It can go anywhere. It's essentially a very irregular or odd electron configuration, one that kind of almost say doesn't make sense. This must be excited, taken up to a higher energy level. So another one here, 1s2, 2s2, 2p6. That 3s1 got taken to 4p1. We'll talk more in depth about this, but this does come up in this unit, so I wanted to make sure that we hit on this before we're done. All right, I think this concludes where we're at. Yep. I'll talk to you later. Come in with any kind of questions and take care.